Good morning, good afternoon, or good evening, wherever you are located, and welcome to the first webinar of 2026 for AMETEK Solid-State Controls. My name's Craig Williams, coming to you from Stafford, Texas, and it's 10 o'clock in the morning here in Stafford, Texas. So the first thing I would like to do, as I always do, is ask if you can hear me. So if you can hear me, please type in the chat that you can hear me loud and clear before we go any further. And just in case you hadn't noticed, we're using a new platform now. So we are using the Teams webinar platform, and let's see how that goes, because Microsoft can be a little bit finicky sometimes. So this is the first time we've ever used the webinar function of Teams. So hopefully it goes smoothly. Thank you, everybody, for letting me know that you can hear me. That is absolutely perfect. So today's webinar is about DC ground faults. We're going to try and do our best to explain everything we can about DC ground faults and all the things that go along with it. Okay. So let me just bring this up. So my name is Craig Williams. I'm the Senior Technical Manager for AMETEK Solid-State Controls. And as I said, I am out of the Houston office. Let me just do this. I've got 24 years in the industrial UPS industry, coming up to 25 years now. And I've been with AMETEK Solid-State Controls for 9 of those years. I've worked with all of the major UPS charger manufacturers. So I'm very familiar with everything that's out there in the petrochemical industry. I worked in the North Sea for, I think it was about 15 years, been on way too many helicopters to ever want to go on one again, going from platform to platform and fixing and installing UPS systems. One of the most popular questions we get asked is, will the webinar be recorded? And yes, it will. Our fantastic marketing team will record the webinar. And it will be posted to our YouTube site, hopefully by tomorrow. London has already posted it in the chat bar. There's a link that takes you to our YouTube channel, and you can view all of the videos that we've ever recorded at that YouTube channel, and you can share them, do whatever you want with them. So they're there, out there for the public, and hopefully there's some good information for you. What we try and do when there are questions and answers is we'd like you to use the Q&A function, not the chat function. If you look at the top of your screen on the left-hand side, you can see chat, and then there's the Q&A function. If you have any questions, if you could please put them in the Q&A function, then I will get to the end of the presentation, and then I will go over the questions that have been asked one by one and hopefully get through all of them. And the webinar should last around about 1 hour. It depends, as always, on how much I speak, how many questions we get. So we will wait and see, but I really try my best to get it all done within the hour. Okay. Let me just do this, just getting used to Teams and how switching between screens goes. There we go there. So the objectives today, we're going to go over DC system basics. Is quite basic stuff, but I want to get a good grounding of what's going on within the DC circuit before we move on to what is a DC ground fault. And then we will discuss how we detect ground faults. And then how you can find the faulty circuit, and then some misconceptions around ground faults. So that's the 5 things that we are going to cover today. Okay. So here's the DC system basics. And sometimes people overcomplicate things. I'm very good at overcomplicating things sometimes. But what I'm going to try and do is break it down to its most simplest form. And I always think the most simplest electrical circuit is a switch with a light bulb. Okay, so on the screen here, you can see that there is, on the left-hand side, there's a circuit diagram, and on the right-hand side, there's a pictorial representation of that circuit. So we have a 9-volt battery supplying a switch that then supplies a bulb. Okay, so obviously when the switch is open, the bulb is not lit, and then when we close the switch, the bulb will light. Now, as you can see on these diagrams, nowhere can you see any connection to ground whatsoever. Okay, and in truth, in 99% of circuits, you don't need a ground for the circuit to actually work. Okay, usually it has no bearing on whether the circuit works or not if there is a connection to ground. Ground gets introduced as a safety mechanism, usually for 2 reasons. The first reason is if there is an a lightning strike on the building, then there is somewhere for that energy to dissipate into the ground, and away from people, and hopefully away from burning up your equipment. And the other reason, safety reason, that we have grounds is to be able to trip a circuit if we have a fault to ground that will prevent fires, and could also prevent a metal case from becoming electrically hot or electrically live and give somebody an electric shock. So that's why we introduce grounds into a circuit. But you don't, 99% out of the time, for a circuit to work, you do not need the ground connected. Okay, we introduce that ground for the reasons that I've just stipulated. Now, obviously, here's a good picture of a switch. So let's pretend that that switch that we had in the previous circuit diagram was the same type of switch as this. It was in a metal enclosure. Okay, so when it's in a metal enclosure, that now gives us the opportunity to make that metal enclosure live electrically if one of the wires inside the metal enclosure came loose, the insulation failed, something happened and touched the case of this switch. So I just want to give you, we'll step by step, we're going through the basics of DC circuits, so you can see what's going on when we get to ground faults. Okay, so now you can see in the circuit diagram, I've drawn the box around the switch, and with reference to electrical code, wherever you're located, it will be stipulated that you bond that electrical case to ground. Okay, so you can see on the drawing here that the system is bonded to ground. There's our ground there, and we have connection right here to the box. So that box is now connected to ground where the switch is. Okay, so still, that doesn't do anything to the circuit. The circuit couldn't care less that that box is connected to ground. It just carries on working. If the switch is closed, the bulb lights. If the switch is open, the bulb goes off. And in truth, if we had a fault on the positive of the battery to the case of that switch, still nothing is going to happen, because all we've done in that circumstance is we have now said that 9 volts there is now connected to ground. I know this is sometimes a difficult thing to understand, but there is going to be no current flowing there. All we've done is said, okay, this 9 volts potential here is now at the same potential as ground. No current is flowing. Okay, when we only have one connection to ground, all we're doing is referencing that point to ground. No current flows at this point. So the circuit carries on working as normal. Okay. The switch is closed, the bulb will light, the switch is open, the bulb goes off. Hopefully you are following this. Now what we're going to do is we are going to put the bulb inside a metal enclosure as well. And remember, with electrical code, if we put anything in a metal enclosure, we have to bond that electrical enclosure to ground. Okay, so now the switch is in its own electrical enclosure, metal enclosure. The bulb is in its own metal enclosure, and they are both connected to ground. Okay. Now, this is where it gets interesting. Now we are going to introduce a ground fault on the 0 volt or the negative side of the battery. Okay. Now we have introduced a problem. And that problem is when you have two ground faults, one ground fault on the positive side and one ground fault on the negative side, what that does is that creates basically a direct short circuit. And here it is drawn here. So basically ground is here. Remember, all these grounds are connected together. So just keep that in your mind. And if positive is connected to ground and negative is connected to ground, that means positive and negative are the same point. It is a direct short, and basically it will short circuit this battery that's connected here. Okay, now if the battery was of a high enough voltage and was a high enough amperage, that would cause high current to flow and could cause cables to burn out, could cause an arc flash at some point. It's bad when you have two ground faults on opposite poles at the same time. So what people have decided to do is we need some way to detect that first ground fault so we can then go in and clear it and prevent this situation here happening, where if you get a second ground fault, you can cause a short circuit, which will cause high current to flow and could cause fire, insulation damage, many different bad things. Okay. So let's put that into an industrial rectifier charger system. Okay. So what we have on the left-hand side is we have our MCC, our motor control center. We're probably going to supply 480 volts from the MCC, and that feeds into the AC input of our rectifier or charger system. Okay. Most rectifier chargers will have an AC input breaker. If it's an industrial charger, it will have an isolation transformer. Then it will go into the actual rectifier bridge, which is usually an SCR-based technology, a silicon-controlled rectifier technology, and that converts the AC into DC. So we have AC on this side and we have DC on this side. And then that usually goes out through an output breaker on the charger, and then there's terminals on the charger that then go out to the outside world. And that outside world is usually a DC panel somewhere in your plant. And that DC panel will have multiple different load breakers, and then it will also have a battery connected through a main breaker there. This is the ideal way that your chargers should be set up to charge your industrial batteries. Okay, so that is the DC system that most people will see inside a refinery, petrochemical plant, or even in a substation. And it's important to go over why an isolation transformer is so important inside an industrial charger system. So let's go back to Electricity 101. And if you know anything about electrical code, you will know that electrical code says that the neutral of a system should be tied to ground on the supply side, anywhere between the transformer on the pole, if it was for a household, or the supply side incomer outside the building. So neutral should be connected to ground. So that's actually done by the Centerpoint, Texas, New Mexico Power here in Houston, or whoever your utility company is. They tie the neutral to ground because that is stipulated in the code. Okay. And then if we have an isolation transformer, you can see here that there is absolutely no physical connection between the primary here and the secondary here. There is no physical connection whatsoever. It is separated. They are two completely separate windings, and it uses the mutual inductance and the fields inside the winding of the transformer, inside the core of the transformer, to transfer energy from the primary to the secondary. Okay, so on this secondary side here, you can see there is no connection to ground, and that becomes very important. Hopefully you'll see in the next few slides. So if you took your Fluke multimeter and you measured between live and ground, or hot and ground, on the primary side, you will measure 120 volts AC if you go between hot and ground. Okay? Because remember, neutral is at the same potential as ground because the utility company put this tie in here. So they are the same point. So if you go between hot or live and ground on the primary side of the transformer, you will get 120 volts if it was a single phase system. Obviously, if it's a three-phase system, 480, whether it's a star delta would affect what voltage you would get. But I like to use single phase because it's much easier to understand. So for single phase, you'll get 120 volts. Okay. Now on the secondary side, yes, between hot and neutral, you will get 120 because the transformer, it's not a step up, step down transformer. It's a 1-to-1 ratio on the windings. So whatever is on the primary will be on the secondary. We have just isolated the two supplies. So it will be 120 volts hot to neutral, and it is classed as a separately derived source. Okay, and what that means is you've created your own brand new power supply to do with what you want. But importantly, there is no connection to ground on the secondary side of this transformer. So if you took that same multimeter that measured 120 volts on the primary with respect to ground, if you went between hot or live and ground on the secondary, what would you see? And the answer to that is, really, you should see nothing. You should see no voltage because there is no reference. There is no potential between hot and ground. This hot here doesn't even know the ground exists. Okay. Now, there can be stray capacitance and other things that can give a ghost potential. So if you ever go between hot and ground somewhere and you see on your meter the voltage starts high and starts to come down, or it starts low and starts to go up, that's usually stray capacitance that is giving a ghost potential, and your Fluke meter is equalizing that potential out, is actually adding some load to that potential and taking the potential away. But in theory, there should be no voltage whatsoever. It should be 0 volts because it doesn't even know ground exists. Hopefully you are following me. So to make it even more simple, if we connect a lamp between hot and ground, not hot and neutral, between hot and ground on the primary, the lamp will light. Absolutely, no question whatsoever. The lamp will light. But if then we connect the same lamp between hot and ground on the secondary of this isolation transformer, the lamp will not light because current can't flow, because it has to get back to this neutral, and there is no path to neutral through this ground. Okay? Very important to understand. And you'll see why in just a little bit. So now we've gone over that on the secondary of this transformer here, we have no connection to ground. So then that secondary then goes into our rectifier. And we've got AC here, and then we've got DC coming out here. And then what we're going to introduce is our positive and negative connected to our battery here. Okay, this is our battery. So we're charging this battery. And then what tends to happen is you need to put the battery on something. What do we put the battery on? We usually put the battery on a rack. And that rack is usually made of metal because batteries are heavy and you need something very strong to keep the batteries off the ground. What they'll do is they will usually coat that metal in some kind of plastic to give insulation. So none of the metal should be exposed. But what the plant will do, because of electrical code, because the rack is metal, they will have to bond that battery rack to the ground of the plant. Okay, so the battery rack is connected to ground, but the battery has absolutely no idea what ground even is. Doesn't care. Absolutely no idea, doesn't care, and doesn't need to know that the battery is connected to ground for the system to work and keep the batteries charged. Ground is irrelevant for DC charging circuits. It's only introduced for safety reasons. Okay, so going back to that same principle, if we take our fluke once again and we go between the positive and the battery rack ground, what should the voltage be? Once again, who knows? It should be 0 volts. It really should be 0 volts, but once again, there can be stray capacitance. There can be something else in the circuit that may give you a funky reading, okay? But there is no, as designed, without any ground fault detection circuit in the charger whatsoever, there will be no reference to ground, and it should be 0, okay? I know a lot of you are screaming at the screen, yeah, but when I go on my battery, I get 65 volts positive to ground and 65 volts negative to ground. We'll get to that in just a moment, okay? And if we went from the negative side of the battery down to ground, once again, there should be no reference. It should be 0 volts, okay? In the most basic of systems that have no ground detection in them whatsoever, and the secondary of the system is not connected to ground, then you should have no reference between the battery and the ground whatsoever. So that's DC circuits explained, that the most basics of them. So what is the most common cause of ground faults? Okay, the usual suspects are worn insulation, conductive dust, water, or other soft ground. So obviously insulation breakdown, that is when the insulation of any conductor, any wire, breaks down, and you can see the copper is here. And if the copper touches, remember, if this was in a metal enclosure, if that copper then touched a metal enclosure, that would mean that that cable is now touching ground, okay, or is now touching metal. So that's the first type of ground fault, is when the insulation on the cable breaks down and allows the actual copper conductor or aluminum conductor to touch the metal case of whatever it could be conduit, it could be a box, whatever the metal object is. The second one, obviously this is extremely exaggerated. I'm guessing this is a paper mill or something like that. I can't remember where I got this picture from, but it is conductive dust. And you can see on the top of this breaker here, there is a huge pile of dust here. And, you know, depending on what the dust is made of and how resistive it is, would basically give you an idea of how much of a ground fault you would have. Because remember, this dust is touching this panel here. Now, yes, obviously it's also shorting across these two cables here, but it would give you a ground fault in this circumstance. Okay. Obviously, that is excessive. It's very rare to see something like this, which is why I put the picture in the presentation. Another one is water. Very common. The amount of DC ground faults that are caused by water in circuits connected to analyzers out in the field is too numerous to mention, because what happens is you have an electrical connection box like this. Now you look at this electrical connection box and it looks like it's epoxy in here, but this isn't an epoxy box. This is actually just a box that has a plastic lid on it, and this yellowy stuff is actually water that's got inside the box. Now this box here is metal, so that means these connections here, if the water is impure and has impurities in it, it will cause a ground fault. Now in this circumstance, it's obviously going to short between the two cables here as well, but it is another example of how you get a ground fault in the field. And then lastly, and probably my favorite, snakes. I just like to put funny pictures in my presentation sometimes, but this is actually taken at a plant. I think this is actually a DC. Oh no, it's not, is it? Because there's an AC receptacle here. I saw the red and the black cable. I thought it was a DC cable connection, but it's not. But obviously, animals do get inside switchboards, especially down here in Texas, and they can cause ground faults as well. Usually when they die. I know that's a sad thing to say, but that usually is what happens. So in its most basic form, a ground fault is when a DC ground fault is when one of the poles of the battery, either the positive pole or the negative pole, becomes connected to ground in some way. And on this picture here, the positive has become connected to ground through that path there. Okay. Now, if it is what we call a hard ground, in other words, it is a very low resistance fault. It's pretty much a short circuit. It's a direct contact between a conductor and the metal case. Then if you took your fluke and you measured between positive and ground, a lot of people would say, well, you'll get the full system voltage. No, you should get 0 volts, because they are the same potential. They are now connected, so there should be 0 volts between them. Okay, so when you're measuring positive to ground and negative to ground on your battery, if you measure between positive and ground and you get 0 volts, then you know you have a positive ground on your system. Okay, ground is connected to the positive pole, or the positive is connected to ground, whichever way you want to say it. Okay, and if you measured between the negative and ground with your fluke, you should see the full system voltage. Now I've shown it as 135 volts. That would be for a 60 cell lead acid system. Okay, because that is the float voltage of most 60 cell lead acid systems, which is the most common in the industrial world. Okay, so you will get the full system voltage between negative and ground. Okay, so you will get, for a positive ground fault, you will get 0 volts if you go positive to ground, and you will get the full system voltage when you go negative to ground. And they're usually relatively easy to find, the hard grounds. Soft grounds, they should be relatively easy to find, but they're more difficult because they have a higher resistance. There is some resistance in the fault itself. Okay, so let's say in this circumstance we have a negative to ground fault, but this time it is a soft ground. So rather than seeing 0 volts between positive and ground, we're seeing in this circumstance around about 15 volts. Okay, so you're not seeing the full system voltage 135 volts, and you're not seeing 0 volts. You're seeing something in between on a soft ground fault. Okay, and then obviously when you measure between positive and ground, you should see the remainder of the full system voltage. So remember, we said the full system voltage is 135 volts. The soft ground was 15 volts from negative ground. So that means we have to see the remaining 120 volts between positive and ground. Okay. Now remember, once again, this is in a system that has no ground fault detection systems in it, and you would have to check it with a fluke to see where the ground, if you have a ground fault, if that makes sense. Hopefully it does. Which leads us in, well, how do we then detect a ground fault? And in its most simplest form, all we do is we create what's called a potential divider or a voltage divider. And we do that by having the most simple form of a ground fault detection circuit is having 2 lamps that are exactly the same resistance in series with each other across the positive and the negative. And then the center point of the lamps here is then connected to ground. Okay. Now remember, on the secondary side, there is no connection to ground. So what we have done in this circumstance is there is no current flowing to ground in this circuit. Yes, there will be a small amount of current flowing through both lamps and back to negative. That's what keeps the lights lit. Okay, now in this circumstance, we're saying that it's a 5-watt lamp, and if you do the math, that means the resistance of each lamp is about 3 kiloohms. Okay, and then you could work out the current that flows through that circuit if you really wanted to. I didn't, so this changes everything. This changes absolutely everything, because now what we've done is we have tied ground to the center point of the system intentionally. We have done this intentionally. And what that means is now if we go in with our fluke and we measure between positive and ground, when there is no ground fault in the system, just when it is running in normal operation, then we will measure 67.5 volts DC roughly. Why 67.5? Because that is exactly half of the full system voltage of 135 volts DC here. Okay, and then if we measured between negative and ground with a fluke, we would get 67.5 volts DC, because this circuit has created a potential divider circuit that has a ratio of 50-50, and it means we have tied this point here to ground, and therefore there will be exactly the same potential either side of that ground circuit. So whenever you go to a system and you measure 67.5 volts on a 60-cell lead acid system, you know that the charger manufacturer has a ground fault detection circuit inside of it. Okay, this isn't some kind of magic that happens when you connect a battery to a grounded or ungrounded system. This will only happen when the charger manufacturer has ground fault detection circuits in its charger. Or there are some circumstances where plants add a ground fault detection circuit like this external to the charger, maybe on a switchgear system. But you will only get the halfway point here if somebody has intentionally created a ground fault detection circuit that connects ground to the center point of 2 resistors. hopefully that explains why most people see 67.5 volts. Obviously, if it's a 120 cell system or a system that gets float charged at 270 volts, you're going to measure 135 volts either side of the battery rack ground. Okay, but remember, once again, no current is flowing between positive and ground or negative and ground. Okay, nothing is flowing to ground. The only current that is flowing is through the lamps themselves. Now, what happens if we do actually have a ground fault? So what happens if the positive does have a hard ground fault and shorts to ground? Okay, well, what's going to happen is this positive point here now becomes the same point here, ground. So therefore, there is no potential across this lamp anymore. There's 0 volts across this lamp. So this lamp will go out. But now we have 135 volts here with respect to this point here, which is 0 volts, which is a negative for the battery. So this lamp will go very bright and it will light. So when this lamp lights, it indicates that we have a positive ground fault on the system. Okay. And then if we have a negative ground fault, that means this is 0 volts, and that means that 0 volts goes to that side as well, which is 0 volts. 0 volts and 0 volts means there is no potential across that lamp whatsoever. 0 volts DC, that makes this point 0 volts. We have 135 volts on this side of a lamp. That means this lamp here will light very bright and indicates a negative ground fault on the system. Now remember, that ground fault does nothing, doesn't affect the operation of a system 99% of the time at all. It's just telling you, okay, we've got a ground fault. If we have a secondary ground fault on the other pole of the battery, that's when we're going to have an issue. This is just for telling us that we have a ground fault and somebody needs to go and investigate and remove it before we have a secondary ground fault that could cause an issue. I'm just going to take a drink. Now that was the most basic ground fault detection circuit, and that was probably designed in the 60s or the 70s, and we've moved on since then. So we now have digital circuits, and we have ways to monitor ground faults much easier. In truth, most circuits will still use a potential divider. They will have 2 resistors of the exact same value in series across the battery. But rather than have lamps, what we do is then we connect it to this alarm circuit control board, and it monitors positive and negative volts with respect to the ground circuit here. And it will use op amps and comparators, and it will give a digital alarm signal. You can change contact relays, or it can send a signal to an LED on the screen. It can send a signal to a DCS panel to say that there is a positive or a negative ground fault. And that's what we use at AMETEK solid-state controls. We use digital monitoring on our DPP and DSE UPS systems. Okay, but it's still the exact same principle. It's just how that voltage being detected is looked at. Rather than just have 2 lamps that light, one lights if there's a fault, now we have an alarm circuit that's monitoring it instead. And there is one other system that you can buy, and it's called a bender. It is slightly different. What this bender system does, it actually injects a very small current signal into the positive and negative, and it keeps doing it I don't know what the duration is, but it's always injecting a signal into positive and then negative, and then seeing if there is a return path for that signal. So if you have a bender system, which is very rare, they're very popular in Europe, but not here in North America. But if you have a bender system, if you measure between positive, and let's say ground is connected here, positive to ground or negative to ground, you are not going to get that halfway point. It uses a completely different system, and the readings you're going to get, I can't tell you what they are. I can't remember if it's zero or a varying signal. I don't know, but it is not a fixed signal of 67.5 volts on either side because of the way that this system works. It does not have the two resistors between positive and negative and the halfway point connected to ground. It doesn't have that. It actually injects a signal into the circuit. I suppose they work good, but it overcomplicates things as far as I'm concerned. The basic resistor network is just so much easier. Okay, so let's go back to the typical DC system and let's see how we can figure out what happens if we get a positive ground fault alarm and what we should do to figure out where that ground fault is. So as you can see here, the charger is saying, okay, I've got a positive ground fault, whether that's the lamp saying positive ground fault or whether it's a digital screen that says positive ground fault alarm. Okay, something has told us that the system has a positive ground fault alarm. So first things we need to know is where is the fault? And the first place everyone starts, because the alarm is on the charger, they always think that the ground fault is in the charger. Okay, very rare that that happens, but we'll get to that when it comes to misconceptions. But it's quite easy to check whether it's in the charger or not, especially if you have these two breakers here. So the first thing I would suggest you would do if you have a positive ground fault alarm inside the charger, and remember, you can do this if your battery is healthy and you know it's good. What you can do is you can open this breaker here. Okay, the battery will continue to feed all of these circuits here and everything is good. And if you open this breaker here and the ground fault alarm clears, that means the ground fault is not inside the charger. It means the ground fault is somewhere out here somewhere. Okay, it's not inside the charger. Now, if you opened the output breaker on the charger here and the ground fault remained, then your next step is to open this input breaker to the DC panel, the main input breaker to the DC panel. Okay, because what that's testing is if there is a fault now between this point here and this point here. Okay, so basically it's testing the external cables and the conduit between the charger and the DC panel. So if you did open this one here and the ground fault stayed, then you know that the cable is bad. But if the alarm cleared, you now know it's somewhere from the DC panel out. Could be down at the battery. So we've now basically, little by little, we're isolating each part. So we're saying, if we open this, the alarm goes away, then it's not in the charger. If we open this and the alarm goes away, we know it's not in this cable. Okay. So next, the most common thing it could be is on the battery. If it's a wet cell lead acid battery, you could have a crack in the bottom of the jar, and that electrolyte could be leaking and somehow tracking down to the battery rack if the battery rack is in poor condition, or if it is corroded somehow, if the battery was misinstalled and there is no insulation between the bottom of the battery and the battery rack. That electrolyte could touch ground and give you a ground fault. So the most easy thing to do then is, if the charger is healthy and online and the charger has capacitors inside it. Now, this is on a case-by-case basis. I'm not advocating, if you don't know what you're doing, do not go out and open this battery breaker here unless you know what you're doing. But in normal operation, especially with modern battery chargers, you can open this battery input breaker, and this charger here will continue to supply all the DC loads to keep whatever those DC loads, to keep the plant operating in normal condition. Okay. And then if you open this breaker here and the alarm clears, then you know that the fault is on the battery. If you open this breaker and the alarm stays, we now know that it's either on here or on this bus here. So once again, one by one, we're moving down the line and we're removing parts of the circuit that could have the issue. So once again, if you open this breaker and the alarm stays, then it's in here. If you open the breaker and the alarm clears, then you can say we have a ground fault on the battery somewhere. Did I say that the wrong way around? I'm just thinking in my head. If you open this breaker and the alarm clears, then the battery has a fault. If you open this breaker and the alarm stays, problem is with the circuits. Hopefully I cleared that up, sorry. So we've decided it's not the charger. It's not the cable between the charger and the DC panel. It's not the battery. People say, well, it has to be on circuit 1, circuit 2, or circuit 3. Well, no, it doesn't. It could be in the DC panel itself. One of the positive or negative cables, either coming in here or here or here or here, could be connected to the case of the DC panel itself. So we need to be able to test that. Okay, and the only way we can do that is by opening circuit 1, circuit 2, circuit 3. Okay, now obviously I understand the plant is probably not going to allow you to do that. You'd have to be in an outage for you to do that because you are disconnecting the circuits, but it is the easiest way to do it. Okay, so open all three, and if the fault stayed, that means the DC panel is the problem, and you have to look in that DC panel and see where there is insulation breaking down. There has to be a cable touching the DC panel somewhere. But if you open all of these and the alarm clears, that means you know that it is now either circuit 1, circuit 2, or circuit 3 that is the problem, and that's where the ground fault is located. Once again, it's just process of elimination. As we move along the line, we eliminate each thing and make sure that's not what's causing the ground fault. And then the last thing is, if it's on the load circuits, then what you would do is you would open circuit 1. If the alarm clears, then circuit 1 has the fault. Okay. Then you would open circuit 2. If the alarm clears, circuit 2 has the fault. If the alarm stays, then it has to be circuit 3. But we would do that by then opening circuit 3. If the alarm clears, circuit 3 definitely has the fault. And it is as simple as that. We've gone through a whole DC system and we now have located the fault. Let's say we did open circuit 3, the alarm cleared, then we know for sure that it's circuit 3, and we now have to get the schematic diagrams out and find out what circuit 3 is feeding. If it's an analyzer in the field, what we would have to do is go out into the field, go to every junction box wherever there is an electrical connection and check it to make sure there is no insulation breakdown, there's no water ingress into that junction box, and find out if it's the actual device that's connected at the very end that has the fault or the cabling in between. Okay. That's the most intrusive way to find a ground fault, because obviously, especially when you come to the load panel, you are probably going to have to take a load outage. But you can do it, what's the word I'm looking for? Unintrusively, using AMETEK BGFT, which is a battery ground fault tracer. And that is a system that you can connect and it will send a signal down the ground fault path, and then you can use a sensor to find out which path that ground is on. So once again, here's our basic ground fault, and once again we have a positive ground fault alarm on the charger. We know that the ground fault is positive. So then what we would do is we would get the AMETEK BGFT main module, and we would connect the positive to the positive terminal and the ground to the ground terminal on the BGFT. Okay, so you connect the transmitter between ground and the pole that has the fault. And then you get the receiver and you put the receiver around the positive cable. Obviously, if it's a positive ground fault, the positive cable going to circuit 1. And then the receiver will tell you if that's where the ground fault is. So if there is no ground fault on circuit 1, what you would do is you would then move the receiver down to circuit 2. Once again, the receiver will tell you through LEDs on the front if there is a ground fault on circuit 2. If there is no ground fault on circuit 2, you would then move it to circuit 3. We said that circuit 3 is where the fault is, so that you would see the LEDs light. It would tell you there's a ground fault on circuit 3. And once again, you would then have to do your checks to find out where on circuit 3 the actual fault is. Okay. It's a great tool, the AMETEK BGFT, because you can look for ground faults without shutting any of the circuits down. Okay. So now we're going to talk about misconceptions. So the first misconception is what I mentioned earlier. The alarm is on the charger, so the fault is inside the charger itself. Now you've got to remember how ground faults occur. It's usually down to faulty insulation, dust, water ingress, and that's going to be very rare inside a charger. Okay. Remember, a charger is an inanimate object. It doesn't move. Yes, it could be, I suppose, somewhere like on a turbine deck. It could be subject to vibration. So in that case, you could have insulation breakdown. But in most cases, the charger just sits there. There is no movement whatsoever. Nobody goes inside it. Nobody messes around with the cables. So it is very, very rare that there's going to be an insulation problem inside a charger. Also, if there is water ingress inside a charger, well, you have bigger problems. That's going to cause way more issues than just a DC ground fault. And if it is really dirty inside, the same again. Yes, you could get a ground fault, but it's probably going to cause shorts on the control board and other things as well. So it's very, very rare that the charger is the actual problem. But obviously, because the alarm is on the charger, it's the first thing that you go to. Oh, my charger has a DC ground fault, so the DC ground fault must be in the charger. Not the case. It could be, but very, very rare. The other misconception: when I measure between ground and the battery, I get weird readings that move. Well, that goes back to that stray capacitance. So that only happens on a system that has no ground fault detection circuits on it whatsoever. It doesn't have the lamps connected between ground, or it doesn't have any kind of circuit whatsoever connected between positive and negative and ground. Okay. Only in those circumstances will you get this weird reading between positive and ground and negative to ground. Okay. And it should be basically ignored unless when you measure it, because what it does is the meter will always either tend upwards or it will tend downwards. It will not stay the same when you put the meter on. Okay. But if you do put your meter on and let's say it stays rock steady at 15 volts between positive and ground and it does not move, then that means you do have a soft ground between positive and ground. Okay. So once again, if the reading isn't steady, it probably means the charger does not have ground fault detection in it, and it's normal. That's what to expect. If the voltage is steady, then that probably means you have a soft ground fault on your system. And the other misconception is, I don't have to worry about ground faults. This system still works okay. You are absolutely correct. I said earlier on in the presentation, one ground fault usually will allow the system to run without any issues whatsoever. Absolutely right. But one ground fault is usually okay. So you can see here, this is a switchgear system. It's a trip and close circuit for a tripping system. So basically, here's the trip coil here, and then here's the safety contacts, and there's a trip contact there. So basically, what we're saying is, if we want the breaker to trip, we have to close the trip circuit, and 52A has to be closed. That's this contact here, and it's connected to this circuit here that basically is monitoring a certain amount of things. And if everything is good, then the station battery, which is usually 135 volts DC, will supply power and trip the breaker, which is a good thing. That's what we want. We always want to be able to trip that breaker, whether we have AC power going to the charger or not. But if we have a second ground fault, that allows, so let's say this DC bus somewhere inside this box connects to ground and the negative connects to ground, we now have a direct short. And look, we have fuses here to protect that. So the fuse will blow if we get that second fault. And that means this trip coil here cannot trip anymore. So we've lost the ability to trip that breaker, which is very, very bad indeed. So that is why it's always important to find that ground fault as soon as you can and remove it from the circuit. Okay, whew, 57 minutes in and I finish. I do talk too much. I am sorry about that. Okay, so now I'm going to go to the Q&A and see if we have any questions. Let's have a look. So we have one question. On an AMETEK UPS, what internally would cause a recurring ground fault alarm? External ground faults are not present on the battery and there is not a DC panel in the circuit. That's a very good question, Jared. That's difficult. One of the most common ways to get a ground fault inside a UPS system is after the DC capacitors are replaced, okay? Because the case of an electrolytic capacitor is usually aluminum, and it is covered with a plastic protective cover, an insulated cover, okay? And some of those capacitors are mounted in the system using a circular clamp. And sometimes due to the position of where those capacitors are inside the system, it's very difficult to loosen the nut to allow that clamp to open up and allow you to remove that capacitor easily, okay? And what can happen in those situations is, what will happen is somebody will go in and they will use brute force and they will grab hold of that capacitor, and they will twist it, twist it, twist it, twist it as they are pulling and pull it out. Okay, removing the capacitor like that, not an issue. But then what happens is you get the new capacitor and you do the same, but in reverse. Instead of pulling, you twist and you push the capacitor into position. Now, obviously, what's happening there, the clamp is usually metal, and what it can do is it can cut into the insulation that is protecting the aluminum can of the capacitor. And it just so happens that the aluminum can of the capacitor is connected to the negative pole of the capacitor. So if you do break the insulation and that insulation does touch the metal of the clamp, and that clamp is connected to the ground inside the UPS, then 9 times out of 10 you're going to get a negative ground fault on the UPS if the capacitor insulation has broken down. We've seen that on quite a few times. So that's one common thing. I can't think of really anything else. I would have to know more about, did it just happen? Has it been that way since installation? Has there been any maintenance performed on it and then the DC ground fault came on? There, as with most things, the devil is in the detail, and I would need to know more about what the circumstances were behind that ground fault coming in. Okay.